About 1 year ago, I made my first video explaining how to make a black hole in Unity that would bend light in a realistic way. Since then, I've been thinking about how to improve the shader, and I've actually found a big mistake as well. So I decided to make a new version of the shader. In this video, we'll implement the black hole as a full screen shader, do some minor improvements, and fix the mistake I made last time. I have a few other ideas to add to the shader, and I'm planning to make this a series of videos. I currently have 7 or 8 videos planned, including this one. I'll be uploading this project to GitHub, so you can download it if you want to take a look at it. Link is in the description. Just as before, I will make a new shader for every episode, so you can open the version that you want. You are free to use it for whatever you want, but I would like you to give me credit if you use it somewhere. Also, if you make something cool with it, feel free to share it in the comments or something. I would love to see what other people come up with to make this look even cooler. When the series is done, I will make the project available for free on the Unity Asset Store as well, so you can simply import it into your own projects. I will add the link to that in the description when that goes up as well. Before we start working on our shader, I'll quickly recap the results of the mathematics we did for the first version of the shader. I won't do the entire derivation again, but I do want to give a list of the equations and quantities we will be using throughout the series. To start, we calculated the orbit of a light ray around the black hole. We found this expression for d phi dr, where b is the impact parameter and m the mass of the black hole. Consider a light ray that comes from infinitely far away, passes by the black hole, and goes back out towards infinitely far away. We'd like to know the total angle this ray sweeps out. This can be done by integrating d phi dr, but since we go from r equals infinity to some finite value of r and then back to r equals infinity, we cannot simply write the total angle as one integral. The orbit consists of 2 symmetrical parts, one where the light ray moves towards the black hole and one where it moves away from the black hole. The point that separates these 2 parts is called the turning point. Here the light ray moves perpendicular to the direction to the black hole. In other words, dr d phi is 0, or equivalently d phi dr is infinite. You can immediately see then that the radial coordinate of the turning point is where everything in these brackets is 0. The total angle swept out by our light ray is then twice the angle swept out from the turning point to infinity, which we can write as a single integral. We then introduce the quantity w equal to b over r, which lets us rewrite this integral into a form that shows that the shape of the orbit only depends on the ratio of b over m. We saw that b is equal to the absolute value of L over E, where L and E are these quantities. Finally, remember that a light ray that is not bent, so just a straight line, sweeps out an angle of 180 degrees, or pi radians. So we define the deflection angle as a total angle swept out minus pi. In the follow-up video, I implemented the correction for the distance of the camera to the black hole, which involved calculating this angle alpha. And the actual deflection angle was then delta phi def minus alpha. That's everything we need in terms of mathematics. Let's take a look at how to implement the black hole as a full screen shader. As of Unity 2022.2, there is a full screen render pass feature in the universal render pipeline. This means that we can implement a black hole as a full screen effect, instead of doing the janky thing with the plane. This opens up some options, which we'll talk about more in the following videos. It's time to hop into Unity. We are currently in a brand new URP project. The first thing we can do is to delete this directional light, we won't need it. Then we can create a folder here for our shaders. In here we can create our black hole shader, so right click, go to create, shader graph, and under URP you will find full screen shader graph. Let's call it black hole shader. And I will add episode 1 at the end because I'm going to make a new shader for every episode. Before we start working on our shader, I will quickly grab the shader subgraphs from our previous video just because I'm too lazy to do it all again. We now have 2 subgraphs, B and deflection angle. Remember from the previous video that we used a pre-calculated texture to determine the deflection angle. So we need to import that texture as well. Let's go back to our assets folder and create a folder for our textures. Then I'll grab the texture from the previous video and import it into our current project. Also, in this shader, make sure that this texture is assigned to the sample texture 2D node. One thing I forgot to show in the last videos was the settings for the textures in the shader. So let's go over those now. If you select a texture, you can see some settings in the inspector panel on the right. For now, we only need to concern ourselves with the compression settings. Since our texture is 512 by 512 pixels, we can set the max size to 512. We don't want this texture to be compressed, so we'll set the compression to none. And don't forget to hit apply or these changes won't be saved. Then also save the deflection angle subgraph and we can close this window. Alright, it's time to get started on the black hole shader. Most of it is going to be the same as before, but because this is a full screen shader, there will be some minor differences. Let's start by getting the view vector. Next we'll do the R vector, which is the position of the camera. We'll normalize it to get the R direction. And take the length to get the R components. Then we'll calculate UR and UPhi just like we did before. Next up is B and the deflection angle. Let's drop these in our shader graph and connect everything. We need a parameter for the mass of our black hole. And it's cleanup time again. Alright, onto the rotation of the view vector. This is also the same as before. We normalize the view vector. And we take a cross product with the R vector. We then use the rotate about axis node. Here is where it gets a bit different. Previously we sampled a reflection probe to get the light in a certain direction, but that didn't work for me in a full screen shader. Instead, we'll sample the skybox directly. The disadvantage of this is that we cannot have other objects in the scene, because they wouldn't be drawn. The advantage is that the skybox can have a very high resolution, while the reflection probes are limited to 4K, so we can get a better looking result. The node we'll be using is called Sample Reflected Cube Map. It behaves the same as a sample reflection probe, but just using a cube map instead of a reflection probe. Everything else is the same as before. So we decompose the vector in the R component and the perpendicular component. We then flip the R components and add them back up. And we use the R direction as the normal. Let's keep the cube map as a parameter so we can change it later if we want to. Finally, we can add a parameter for the environment brightness and cut out the black hole. And one final cleanup time. Before I forget, let's add proper default values for our parameters. We now made our shader, but how do we use it? Well, first off, as with all shaders, we need to create a material. You can right-click on the shader and go to Create Material, and the new material will be created using the black hole shader. I like to have my materials in a separate folder, so let's do that. Now we need to choose an environment. I bought an HAR environment from Tim Barton. I'm a big fan of his work and you should definitely go check out his ArtStation. Since I bought a non-exclusive license though, I won't share the skybox, and so it won't be included in the project. You'll have to find an environment yourself. In any case, once you have an environment, import it into your project. There are some texture settings you need to change. First off, change the texture shape from 2D to cube. You can leave the mapping on auto. My HDRI is 16K by 8K, which is the largest Unity can handle. So let's set the max size to 16K. You can play around with the compression quality settings and see if they make a difference, but I just set it to high quality. And again, hit apply to save the changes. If you use a high resolution image like I did, it may take a minute for Unity to compress the image again. Let's go to our black hole material and assign the skybox. To use the material, we need to change some settings in the universal renderer data. If you started from the URP project presets, this should be in a folder called Settings. And you should have these 6 files. 3 URP asset files and 3 universal renderer data files. These are the 3 quality levels that come with the URP preset: Performant, Balanced, and High Fidelity. We are using High Fidelity, so click on this file, called URP High Fidelity Renderer Asset. In the inspector panel, all the way at the bottom, there should be renderer features. We can delete this screen space ambient occlusion, we won't be using it. And then click Add Renderer Features and choose Full Screen Pass Renderer Feature. The material, we can choose our own material, called Black Hole Shader. And for the injection point, we want to use before rendering post-processing. And let's give it a name. Let's call it Black Hole Pass. For some reason, when I look in the scene now, I see this gray environment. It turns out that if you go to the black hole shader in this cube map, you need to set its default value to our skybox. And this should fix the problem. I don't know why this is the case, but apparently this is how it works. I quickly want to mention how to enable anti-aliasing, since it was a bit confusing to me. There are 2 different places where you can enable anti-aliasing, and they don't work together. The first place is Universal Render Pipeline Asset. If you started from the URP project presets, this should also be in the settings folder. Select the URP High Fidelity Asset file, and under Quality, you will find anti-aliasing. This should be disabled. If you enable this, Unity will use the MSAA anti-aliasing, which doesn't work for the shader aliasing. The second place to find anti-aliasing settings is on the main camera. If you select the camera, under Rendering, you will find the anti-aliasing settings. There are 3 different anti-aliasing algorithms you can choose from. You can experiment with them and pick which one you think looks best. I picked SMAA, not to be confused with the MSAA from before. There is a page in the documentation of URP that explains all of the anti-aliasing methods. I'll put a link to that in the description. At this point, we have replicated exactly the black hole shader from the previous video, but now using a full screen shader. However, as you can see from the length of this video, we are not quite done yet. There is something I would like to change about our texture. Last time I decided to use the horizontal axis proportional to 1 over b and the vertical axis proportional to log r. To use log r though, we needed to decide on a maximum range for r. I don't like to have a built-in limit like this, if we can at all avoid it. So instead we'll use a vertical axis that is inversely proportional to r, just like the horizontal axis for b. We can easily adjust our code for calculating the texture to do this. All we need to do is to go down here, where we define r, and replace it with the line above. And then change x to y, and this number to 3. That's it. We then also have to go into the shader and change the UV coordinates to use 1 over r instead of log r. So we get rid of all of this, and duplicate this divide node, and connect r over m, and replace this number with 3. Now, there is one small technical detail I'd like to point out. Well, two actually. In Unity, when you read off a texture, you don't necessarily just read off the value of a pixel. Say we are reading from a texture at a certain UV coordinate. Usually, that UV coordinate does not fall precisely in the middle of a pixel. In general, the UV coordinate will be somewhere in between the center points of 4 pixels. Now, there are multiple ways to determine what the value is at this point in the texture. One way is to just return the value of the nearest pixel. This is precisely what I meant earlier with reading off the value of a pixel. What Unity does by default, however, is interpolating linearly between the values of these 4 neighboring pixels. In most cases, this is preferable to returning the value of the nearest pixel. You can choose the way Unity interpolates between pixels for each texture in your project. It's in the same place as the other texture settings we discussed earlier. So just click on the texture in the asset browser. In the inspector panel there is this setting called filter modes. By default this will be bilinear. There are 2 other options, point, which is no interpolation, so just reading off the nearest pixel, and trilinear, which is some other kind of interpolation that I don't really know. We'll use point for some other textures in the future, but for this one, it's actually better to leave this on bilinear. All this is to say that there is some interpolation going on between the pixels of our texture. So it's a good habit to avoid discontinuities in our textures near edge cases, like for example b equal to square root of 27. For all our textures, we're going to think about edge cases and how to avoid discontinuities. Coming back to our code, there are some changes we want to make. Before we start, I should warn you that we're not gonna care about efficient code, because this code is only meant to run once. Sensitive viewers might want to look away. First off, since the first row of our texture is r equals infinity, we want to handle it separately, just to be sure. Our main loop will then start at 1 instead of 0. The first column is b equals infinity, so the entire column should be 0. So also here we can start at 1. To get rid of the discontinuity, we can first fill the entire texture with the minimum deflection angle. And then in our main loop, we'll first check if the pixel is valid, and only if it is, we'll replace the value with the actual deflection angle. Checking whether the pixel is valid or not is pretty easy. We just look if w is greater than the turning point. While we're on the topic of technical details regarding reading off of textures, there is, you guessed it, another technical detail. This time it has to do with the UV coordinates of the texture. Imagine we have a texture of n by n pixels, where on the horizontal axis we have some quantity x, with values ranging from 0 to 1, and on the vertical axis we have some quantity y, also ranging from 0 to 1. In order for the interpolation between the pixels to make sense, we want the values of x to correspond to the centers of the pixels, and the same goes for the values of y. So this means that if we would use x and y as the UV coordinates, like we have been doing up until now, we are actually making a bit of a mistake. X equal to 0 should correspond with u equal to half the width of a pixel. Similarly, x equal to 1 should correspond with u equal to 1 minus half the width of a pixel. And the same goes for y, obviously. The width of a pixel is 1 over n. We can then express x as n minus 1 over n times u plus 1 over 2n, and y as the same, but with v instead of u. So what this means in practice is that we need to rescale our UVs like this, before we access a texture. Let's add that to the shader. So we create a new subgraph, let's call it UV Pixel Center Correction, which takes in the UV coordinates and the resolution, and returns the new UVs. Then we just multiply the input UVs by n minus 1 over n, and add 1 over 2n. In the deflection angle subgraph, we then add the correction to the UVs. The last thing I want to do in this video is to correct a mistake I made last time. When we calculate B, we use u-phi and ur. We calculated ur by projecting the view vector on the vector pointing from the black hole to the camera. We then subtract ur from the view vector to get the perpendicular part, which we said was u-phi. This is wrong. u-phi is indeed perpendicular to ur, but if we do it this way, the length of u-phi is wrong. To see why, let us first write out what we are doing mathematically. Let's assume the light ray is in the xy plane, just to make the mathematics a bit easier. We then have a camera position and a light ray in a certain direction, which is the view vector. Let's call it v. V has two components, vx and vy. Alternatively, we could use a different coordinate system using vr, which is the component in the r direction, and v-phi, which is the component perpendicular to the r direction. This is what we do currently in the shader. Remember from the first video that we expressed the path of a light ray in terms of a parameter lambda, which expressed for a certain point on the path how far along the path it is. ur was then dr d lambda, and u-phi was d phi d lambda. Coming back to our vector v here, we can see that vx is dx d lambda, and vy is dy d lambda. We now want to express this in polar coordinates to get ur and u-phi. Let's start by writing out x and y in polar coordinates. We can then differentiate both sides with respect to lambda. For simplicity, we will now assume that x equals r and y equals 0. Doing so reduces these equations a lot. So we see that dx d lambda is the same as dr d lambda, which makes sense since this point is on the x-axis. Looking over at dy d lambda, we see that there is this vector r in front of d phi d lambda. This is the important part, and it holds for any point xy, not just for a point on the x-axis. The only thing that changes if we pick a general point xy is that instead of x we get r, and instead of y we get the component perpendicular to r. So we can replace dx d lambda with vr, and dy d lambda with v-phi. By definition, dr d lambda is ur, and d phi d lambda is u-phi. We can see now that using vr as ur is correct, but using v-phi as u-phi is not. We need to divide v-phi by r. That's easy enough to correct in the shader, we just need to add a divide node here. And connect r. We now have the black hole implemented as a full screen effect. It should look exactly the same as before, except for the change in U-phi, which makes the black hole appear larger than before. Thanks for watching. If you enjoyed this video, stay tuned because there is a whole lot more coming.